Good evening, everybody. Yeah, it's wonderful to see such a wonderful turnout. Thank you all for coming. Welcome to this first Studium Generale lecture of this academic year. And my name is Jaap Jansen. I'm program maker at Studium Generale. And Studium Generale is a platform of the university that organizes lectures, debates, lecture series, cultural events, film and talk evenings about a very broad variety of topics. And the guest speaker of tonight is Samaya Nissanke, and I thank you for coming to Maastricht and for joining us as well. Thank you. And her research focuses on understanding astrophysics of strong gravitational fields around compact objects, which is very crucial for understanding the evolution of our universe. And nowadays she's working on the merging of compact double systems like neutron stars and white dwarfs. And she is also trying to map the expansion history of the universe using multi-messenger astronomy. And that she will explain, probably in the lecture, what this means. Samaya Nissanke is an associate professor of gravitational wave and multi-messenger astrophysics at GRAPPA, and GRAPPA stands for Center of Excellence in Gravitation and Astroparticle Physics, and that's part of the University of Amsterdam. She's also a member of NICEF, the National Institute for Subatomic Physics, and a lot more, and she won a lot of awards, but I won't mention it all. So please give her a warm applause. Samaya, the floor is yours.
So, good evening, everyone. I hope you can hear me. I told Jaap I have quite a loud a loud projecting voice, so I hope I'm not booming you all at the back as well. But I would firstly like to say a big thank you to the organizers for inviting me. Secondly, a big thank you to all of you for coming on an 8 p.m. on a Monday evening. I really appreciate seeing the audience and all of you here, and I'm really excited to tell you about black holes and gravitational waves, especially in one of the possible future homes and sites of the next generation gravitational wave observatory, the Einstein telescope. So it's really such an honor to be here, and especially at this time in this very rapidly exploding, observationally driven field of multi-messenger astronomy. Now, what do I mean by multi-messenger? I'm talking about observing cosmic events using the radiation from the entire electromagnetic spectrum. Sorry, where's my pointer? As well as gravitational waves, as well as high-energy astroparticles. And I'll be talking here in the next 45 minutes to an hour about work that I've done, as well as work performed with various collaborations, gravitational waves, as well as electromagnetic collaborations, and in particular, work done within the Virgo collaboration that operates with the LIGO Virgo KAGRA scientific collaboration. And as Jaap mentioned, I am a member of the NICEF Gravitational Wave Group. So shown here is a collage of all the different individuals. I should mention, in terms of the gravitational wave detectors and collaborations that I'm talking about, they are now typically about 1,000 members involved. So really the results I'm talking about are thanks to decades of hard work of really hundreds of scientists. But in the Netherlands, these are the gravitational wave scientists, and especially I would like to highlight my colleagues and wonderful collaborators here in Maastricht. You have a very, very blossoming and growing gravitational wave effort in Maastricht, and I would of course like to point you to them in case any of you would actually like to do research on gravitational waves or find out about gravitational waves. There are many members also in the local community. I'm not sure if any of them are here today, but really just to strike how important the work here, as well as going for the preparations of Einstein telescope, is happening. Okay, so what do I mean by gravitational waves? Well, let's go back to general relativity, where in 1915, in Albert Einstein's seminal paper, seminal paper, he showed that space-time, we are not only living in a four-dimensional space-time, but space-time itself is a dynamic quantity that expands, contracts, and curves around matter. And this is exemplified in the so-called Einstein field equations here, where on the left-hand side, this is an expression for the space-time curvature. On the right-hand side, we have g, Newton's constant, c, the speed of light, and this quantity t mu nu represents the mass energy of a source or of an event. So essentially, what Einstein's field equations and the theory of general relativity are telling us is matter tells how space-time curves, and space-time itself tells matter how to move. Okay, so these are intrinsically related. Now, importantly for gravitational waves, I'd like to highlight this quantity g mu nu. This is called the metric, but what it embodies is the geometry of space-time. Okay, so within a year of the publication of Einstein's field equations, there were two important consequences that were realized with regards to general relativity. The first was discovered within 6 months of the publication by Carl Schwarzschild in the trenches, actually, of World War I, where he discovered the first analytical solution to Einstein's field equations in vacuum. And this Schwarzschild metric essentially describes the space-time around a spherically symmetric mass, or indeed a black hole. And black holes are the extremes of space-time curvature that we know of in the universe. Indeed, if you compress the Earth to essentially the size of a grape, okay, 1 centimeter or so, we would end up with a black hole. They have no surface, okay, they just have an event horizon that's separating information within the black hole from the outside universe. And they are essentially the most fundamental and simple objects that we know of in the universe. Astrophysical black holes are entirely described by two numbers: the mass as well as their spin, their angular momentum. Okay, so you just need two numbers to describe black holes. And they are, and sometimes, and this is why we actually describe them sometimes as sort of gravitational atoms of the cosmos. Now, the second important consequence, in addition to the existence of objects such as black holes, was actually shown 7 months after the theory of general relativity was published by Einstein himself. Where in this paper, as you can see, Einstein shows that if one actually breaks this metric that I showed earlier, this geometry of the space-time, into essentially a background metric, as well as what we call a perturbation metric, basically describing a wiggle or a ripple on this background metric, the Einstein field equations themselves reduce to what is a wave equation in this ripple, okay, in the ripple of the space-time fabric itself. And so, indeed, he himself showed that there should be the existence of gravitational waves, these ripples in the fabric of space-time themselves that are traveling at the speed of light. Okay, and they're sourced essentially by accelerating asymmetric matter sources, so essentially pairs of black holes or neutron stars orbiting around each other, as you can see on this 2D visualization, where you see these gravitational waves are essentially taking energy and angular momentum away from the system. So I'll show it again. So you can see the two black holes here, and then you can see these ripples in the fabric of space-time itself, carrying energy from the system and making these systems in spiral and finally merge. And so they start merging faster and faster, and it's these waves that we call gravitational waves. Now, typically, the wavelength of these gravitational waves are much larger than the typical size of the source, and we therefore call them actually coherent, hence the analogy to sound. You may hear people saying we're actually listening to gravitational waves. They're also weakly interacting, which means that they're very difficult to detect on Earth, as I'll describe, but they're also essentially travel to us unimpeded, allowing us really to probe the bulk dynamic properties of the matter itself. Okay? And so this is really what makes them unique probes of the universe. We are understanding and we are using them to basically measure quantities or these black hole properties and neutron star properties that we cannot obtain from light, from traditional electromagnetic spectrum. They have, and so you can think of these sources basically as like your rotating dumbbells that you have in the gym or that you may use. And now observable is this gravitational wave strain. Okay, this is a dimensionless, that means there is no units attached to it. It's a dimensionless strain, time-dependent strain, which has a 1 over distance to the source dependence. And this is very different from traditional astronomy, where we're measuring fluxes of light, which have a 1 over distance squared dependence. They also have two polarizations, H plus and H cross. Okay, and these are essentially the lines of force that are acting as a gravitational wave is passing perpendicular to the test particles. Okay, so what I'm showing in this movie here is the action of a gravitational wave as it passes through a ring of circular test particles, and you can see this stretching and squeezing of matter happening. Yes, so this slinky is basically our gravitational wave is passing through here. Okay, and you can see this tidal stretching and squeezing perpendicular to the direction. And so gravitational waves are acting as this tidal stretching and squeezing. And this is indeed the principle on how these gravitational wave detectors are actually measuring gravitational waves at the moment. In the kilohertz regime on the ground, at the moment we have 4 kilometer length interferometers, the LIGO detectors in Washington State, in Louisiana, as well as the Virgo detector, which is a Franco-Italian as well as Dutch, as well as several other European partners, a 3-kilometer detector in Pisa, as well as a new Japanese detector being built in the Kamioka mine. And the way these detectors are working are that they are actually trying to measure this tidal stretching and squeezing of space-time as the gravitational wave passes through. Now, in the next 5 years, the hope is that we're also going to be building another 4-kilometer detector in LIGO, India. And the reason why we want to expand this worldwide network is actually to try and pinpoint where the gravitational wave source is coming from in order to actually try to observe any light that may be emitted from these compact object mergers, which I will discuss. I haven't so far said anything about what kind of strain size we should expecting or measuring, and at the moment the dimensional strain is about 10 to the minus 21, which means that we are trying to actually measure changes in the arm length, okay, of these kilometer length laser interferometers of about 10 to the minus 18 meters. Now, to put this in another way, that's 1,000th the size of a nucleus of a hydrogen atom, okay? Or indeed, if I was trying to measure the change in distance from Earth to our nearest star to the sun, Alpha Proximus, yes, which is 4.25 light years away, it would be trying to measure that change in distance to the thickness of a hair. A piece of hair, yes? And so this is the technology that we have actually managed to achieve after decades of hard work on instrumentalists as well as engineers to actually be able to build these detectors. I just think it's absolutely mind-blowing when you think about what we have actually able to achieve. And so I just want to zoom in to give some flavor of how these detectors are working, these laser Michelson interferometer detectors. And so as I mentioned, we're trying to essentially measure the combination of the two gravitational wave polarizations, which are stretching and squeezing these space-time ripples, okay? And so what you see in this movie is you will see the laser light being generated, and it's going to be hitting this beam splitter, which will actually split the light into two equal and separate amounts, which will then travel down these kilometer length, 3 kilometer or 4 kilometer arm lengths, to distant mirrors, and which will then reflect back the light at the beam splitter. And so these two arm lengths are perpendicular to each other. So you will see this in this movie. Okay. And then as a gravitational wave is passing through, in this case going from up to down, you see the mirrors basically changing. This is hugely exaggerated because, of course, these are infinitesimal changes that we're trying to measure. And as a gravitational wave passes through, we then detect this at a photodiode as essentially a flickering of the light. Okay, so I will show this movie again. But here you can see as the gravitational wave passes through, one arm length is being stretched, the other arm length is being squeezed, and this is continuing. This is why I'm waving my hands slightly in a weird way, but this is really to impress upon you that this is what we're measuring, this tidal stretching and squeezing of the space-time. So I'll show this again. The second half of the movie is showing how the light flickering is actually detected, essentially by using interference of the light. Yes, so if there's no gravitational wave present, the arm lengths between the beam splitter and the mirror are precisely monitored such that when the waves combine at the beam splitter, they cancel each other out, so there is no light observed. But when a gravitational wave passes through, then you see constructive interference as the light goes in phase, they add together, and you will see this flickering of the light that is being measured. Okay? And so let's go back to 2015, okay? And this was really, I was a bit surprised today to realize this was actually 9 years ago. This Saturday, where we actually first observed gravitational waves from a pair of black holes actually merging 1.3 billion light years away, okay? They were detected on Earth on September the 14th, 2015. we believe, and we've inferred, that the masses of the black holes are such that one is 29 times the mass of our sun, the other is 35 times the mass of our sun. These are basically city sizes. And the signal itself actually only lasted 0.2 seconds. So I'm going to show this movie. So this is a simulation to show this first event. And within those 0.2 seconds, the luminosity, or the energy per second that was released, was 50 times that of if you summed up all the observable light from all the stars and all the galaxies in the universe. It was the most luminous event that we had ever seen. Okay, in those 0.2 seconds, 3 solar masses of energy, so that's 3 times the mass of the sun, was released. Okay, so really phenomenal. I will show it one last time. But yeah, it was mind-blowing. And the fact that we could actually relate this to this cosmic event that happened 1.3 billion light years away, I think still blows many of our minds when we think about what we are learning. And so these were detected at the time by the LIGO detectors in the US. The Virgo detector in Pisa was not operating in 2015. It joined in 2017. And what I'm showing here, I think, is one of my favorite depictions of gravitational waves. This is an actual signal from the first event. Okay, and so shown here is a time frequency spectrogram. What you're seeing here is the actual signal that was detected, okay, above the detector noise in black. And what you're seeing in the bottom here is actually this dimensionless wave strain, this h of t that I mentioned. And we see about 8 cycles happening before the actual merger. Okay, and so these are the 2 signals that were seen in the Hanford and Livingston detector. And what I'd really like you to also focus on is this ever-increasing kind of swish that you're seeing, a kind of Nike swish, yes, this ever-increasing frequency and amplitude of the signal. And it's this that we were able to actually extract a lot of information from. And also, I will play to you the signal now, if it works. So the deeper one is the actual data. The higher one you're hearing at higher frequencies is just tuned so that it's more audible in the human audio band. Okay, but what can we actually learn? Okay, it's fantastic, you've shown us the signal, but what have we been able to actually learn from these measurements, okay? What kind of information about black holes are we actually learning? And so in order to pull out information or retrieve information like the masses and the spins, remember those 2 numbers I mentioned about black holes that characterize them, we essentially take the signal, which is shown in blue here, yeah? This is the wave strain as a function of the time, okay? And we basically filter this with template banks of what our predicted signal would actually look like, okay? And we then vary parameters such as the mass or the distance, okay, accordingly until we find the best fit prediction, which you see happening here. Yeah, so I will play it again, but you can essentially see how we vary the distance and the total mass, and how this can change the prediction of the waveform until we find this best fit waveform. And this is indeed how we are pulling out the information, such as the masses, the spins, the distance to the source, etc. But we, of course, rely on these predicted wave strains and what we call gravitational waveforms. This is actually what I started doing my PhD on. I apologize because I'm struggling to find you might find it more the cursor, but these are the gravitational waveforms. These are the predicted wave strains that we're actually looking for. And broadly speaking, they comprise these three phases, the so-called in-spiral, the merger, and the post-merger, or the ring down of the final object that happens after the merger. Okay, and this really describes the final minute or seconds in the lifetime of these pairs of black holes or pairs of neutron stars. Now, for black holes, pairs of black holes of tens of the times the mass of our sun, we are most sensitive to the actual merger phase in the middle. We only saw those 8 cycles, as I mentioned, where we rely on what we call numerical simulations or numerical relativity to actually model the merger. And so I'm going to show you an example of such a numerical relativity simulation of this first event. So we're looking at our universe, which is depicted on this two-dimensional surface, and you can see the warping of the space-time by the black holes as they go around each other. The colors are showing essentially the slowing down of time. The green with this time is being slowed down by about 20 or 30%, and the arrows are showing the space-time actually being dragged around by the two black holes orbiting each other, the orbital motion of the black hole. And at the bottom, you can see the predicted wave strain from these computer simulations that are solving Einstein's field equations, that equation I showed you at the very beginning, directly. Okay, so during the merger, as the two horizons touch, the movie pauses, and you then see this final remnant black hole. And throughout the movie, you should be seeing basically these ripples, okay, or these wiggles in the space-time itself, carrying away that 3 solar masses of energy. Okay, so typically these simulations on the most sophisticated high-performance computing facilities that we have can take several months just to run one of these simulations. Okay, and of course this first discovery resulted already in 2017 for the Nobel Prize in Physics that was given to Ray Wise, Barry Barish, and Kip Thorne for their decisive contributions to the LIGO detector and the observation of gravitational waves. And what I would really like to emphasize, this was something I read a few years after the detection that I think is really remarkable. Remember I said these things happened 1.3 billion light years away. But as the waves themselves hit our own galaxy, the edges of our own galaxy, this was the time when Neanderthals and humans were mixing, yes? And in the 50,000 intervening times, the 50,000 years intervening period from those gravitational waves hitting our Milky Way to us detecting them in 2015, you know, humans basically developed human-gatherer tribes, developed language, mathematics, and actually the ability to understand this concept of space-time, understand the concept of actually seeing these ripples in space-time and actually then building these detectors to actually observe the event, which I think is just quite phenomenal on a kind of cosmic scale. So today, where are we at? So what I'm showing here is a summary of all the different gravitational wave chirps, okay, those signals that you saw that were seen from 2016 to 2020. So on the top row, you have 01. This is our first science run in 2015 to 16. 02 is our second science run in 2017 when Virgo joined. And 03 operated from 2019 to the beginning of COVID. Okay, and you can see that because the detectors increased in sensitivity due to upgrades, we were able to see many, many more events. Yes, and you're seeing that there's a diversity of different swishes, of these different chirps happening. Okay, so at the time of COVID, we had about 90 published events. And if we think about what we've learned from those events, what I'm showing you in this diagram is essentially the gravitational wave masses of the mergers of the black holes and neutron stars that we've seen. So on the y-axis, we have the masses in solar masses. The horizontal axis doesn't have any meaning. The blue bubbles and the orange bubbles represent black holes and neutron stars, respectively, that we have observed in gravitational waves. And those arrows are pointing to the final merger product. Okay? And you can compare these to the red and the yellow bubbles, which are the black holes and neutron stars that were previously inferred, okay, from electromagnetic observations before. That was sort of the state of our knowledge before 2015. Okay, so these blue and these orange bubbles, our gravitational wave observations, are really beginning to probe and show the diversity in the fundamental properties of stellar mass black holes and neutron stars, the end state of the most massive stars that we know of in the universe. Okay, and so these are the 90 published events. I will tell you in a few slides about where we are today. But before going forward, I'd like to actually spend some time on the event that's marked in red here, a pair of neutron star mergers that was observed on the 17th of August 2017. This is given by the number. Okay, and what made this special was it was the first time we were seeing a pair of neutron stars, not black holes, that were merging, and the first time and the only time so far that we've actually observed light coming out with the event. Okay, and this allowed us, for the first time therefore, to actually pinpoint where the gravitational wave happened in the sky. And so this really was our first, and to date, only multi-messenger discovery that we've seen in gravitational waves and electromagnetic light. And it's a field I've been working on over the last 20 years or so. But why are we interested in neutron stars? I've told you how exciting black holes are. Well, neutron stars, like black holes, are also the end product in the life of massive stars. But they are not only the extremes of space-time, but also of dense matter. They're material about 1 to 2.5 times the mass of the sun, okay, that are crammed into objects that are the size of our typical cities. Yeah? And this means that the densities are as high as if you cram the entire of humanity into a sugar cube. Okay? Whoa. Yes. So when you merge or bash these two neutron stars together, they're in some sense, remarkable astrophysical particle colliders in themselves. They're not happening on Earth, but they're happening out there in the cosmos. Okay, and they were first discovered by Jocelyn Bell Burnell. The Nobel Prize in 1974 was for the discovery of pulsars. And of course, there was another Nobel Prize given to Joe Taylor and Russell Hulse for the Hulse-Taylor binary, a pair of neutron stars that were in a really gradual in-spiral around each other, which resulted in the first sort of indirect detection of gravitational waves. We could see by the way they were orbiting that they were, from their orbital motion, that they should be losing energy according to general relativity. And so this resulted in the Nobel Prize in 1993. And what I'd like to discuss in the next 10 minutes or so is how this one event, this merger of those two neutron stars, resulted in multiple breakthrough discoveries that impacted many different fields, both in astrophysics, cosmology, nuclear physics, as well as gravitational physics, okay? And where we are going in this direction. So the music is really loud, so forgive me, but I will go back to August the 17th, 2017, where this first binary neutron star, or pair of neutron stars, was observed. It happened 130 million light years away, okay? And you can see the neutron stars going around each other. So what made it so dramatic, okay, is because not just the music and the NASA movie, but also because these neutron stars actually had matter. So during the complicated merger, okay, compared to just these black holes, which are singularities or punctures in the space-time, there was actually some matter thrown out from the system, which you can see in the movie. And there were two types of matter being thrown out. One as a relativistic jet, that means a jet being thrown out nearly at the speed of light. And the second was this basically metal-rich cloud, this initially very neutron-rich material that underwent what we call rapid neutron capture nucleosynthesis. Basically, this acted as a radioactive source of heating. Okay, you saw that big gas cloud, which I'll show again. And these systems had been long hypothesized to be the production sites of where our heavy elements come from in the cosmos. So I'm going to just show you how we actually could see that, but I'll just show this movie again. So first you see the gravitational waves happening. And so for this event we saw 1 minute in band. So you see the jet, and then you see this metal gas cloud being emitted, okay? So this allowed for these multiple discoveries, which I'll talk you through. First, the first observation of gravitational wave and light, the electromagnetic radiation coming from these two different types of matter outflows. The second was that actually detecting first the gamma ray as well as the optical flash meant that this led to the most unprecedented campaign, observational campaign by ground and space-based telescope. I think every single instrument that we had observed this system. It's the most well-studied astronomical kind of transient event that we have data sets for. And it was observed basically in every wave band at different frequencies. So you can see days at the bottom, and when the different frequencies were seen. So the X-rays at 9 days, and then the radio popped up. Okay? And by observing the electromagnetic counterpart, we were able to actually localize which galaxy it happened, and I will show the kind of inference that we were able to actually make from that observation. But first of all, I would like to go back to that wiggle, the wave strain, and compare it to several other pairs of black holes that we had detected. And in the bottom, you will see the binary neutron star as a function of how much observing time we saw it compared to the first event, which was 0.2 seconds. We tracked thousands and thousands of cycles because of the relatively low mass of the system. So about 4,000 cycles were tracked as opposed to 8 cycles, which allowed us really to make quite detailed measurements on the masses as well as the actual nature of the extreme dense matter of these neutron stars. Okay, and so just a reminder, why are we so interested in measuring gravitational waves and electromagnetic radiation from these systems? Well, from gravitational waves, because of the wave strain, depending on the fundamental properties like the masses and the spins of these systems, we are really just relying on general relativity to be correct. We don't have to worry about the messy astrophysics in some sense when we make these gravitational wave measurements. And from the electromagnetic side, we can actually infer information about the environment as well as the energetics of the event. And so we kind of need all the pieces of the jigsaw puzzle to put these systems in their true astronomical and cosmological context. And we can also use the electromagnetic counterparts to do fundamental physics, as I'll describe. So one of the amazing things was in those first 2 seconds, we were able to actually constrain the speed of gravity to the speed of light to 1 part in 10 to the 15. So what you're seeing in the bottom is the gravitational wave chirp for this event, and in the top you will see the gamma ray bursts that were detected 1.7 seconds after the event. Okay, so already in the first 2 seconds we could do the first time this quite fundamental test about understanding the speed of light and gravity. And interestingly, and just on a personal note, I was looking at this time frequency spectrogram about a few minutes after the event at the University of Amsterdam. I was quite astounded actually, because the day before we had just had an international conference in Nikef where I'd been asked to talk about multi-messenger astronomy in the 2030s. We had not seen anything yet, we'd just seen binary black holes. And I had made the statement, if we talk about the 2030s, we have to talk about the 2020s. And I think that there will be several gravitational wave and electromagnetic observations of neutron stars, binary neutron stars being measured. And at the lunchtime, just before this event, half an hour before this event, my colleague, the head of the LIGO India collaboration, said, "Samaya, I love your enthusiasm, but I just don't think this is going to be seen by any of our detectors before 2021. And I took a hand-shaken bet, a gentlewoman's bet on this, and half an hour later I was looking at the signal, which we could already tell from just the nature of the time frequency of this chirp that we were looking at something that probably had a pair of neutron stars. And then of course the gamma ray burst was announced at the same time. Okay, and so the fact that we actually had 3 detectors working, similar to GPS, we can use the arrival time of the detectors to actually triangulate where the source was happening. And so this is shown in this video here, where we could localize it to what we call 30 square degrees. That's 400 times the full moon size, okay? And with the distance measurement, this was something also I had proposed with my collaborators earlier, we could build these gravitational wave volumes and cross-match them to known galaxies in that volume, which actually enabled observers to go ahead and rank list galaxies in terms of how heavy or how bright they are to see if they could see a flash. And in this case, a bright blue flash was seen at 11 hours in the galaxy NGC 4993, which is in the Hydra cluster. Okay, and this was absolutely mind-blowing. So this is all happening in real time, yes? That we actually are detecting what is the radiation coming out from this system. And it was actually the monitoring over 2 weeks of the ultraviolet, the infrared, as well as the optical that allowed us to say that this event was unlike anything we had ever seen before. So what I'm showing in this movie is actual real data taken by the very large telescope in Chile by the European Southern Observatories. And you're going to see this movie of the data as a function of days. It starts off, so you see the brightness as a function of wavelength. the snapshot that you're seeing is actually very typical, this featureless blue spectrum of a typical photosphere of a star, yes, or a black body. And as this movie happens, you will see as the days progress, it rapidly evolved to longer, redder wavelengths, and you start seeing these broad line absorption features, okay? And these features were actually the fingerprints of heavy elements that were predicted to come from these mergers. Okay, and so what do I mean? I'll let the movie play. Yeah, you can see we had quite a lot of data of this event before it became too faint to actually detect. But what are the heavy elements that were actually synthesized by that metal-rich gas cloud? I will show you here. These are the elements shown in yellow that we were able to actually connect with being formed in this colliding neutron star. So for the first time, we could say that elements such as gold and platinum, and this is why these events, you may have heard them being called bling nova or kilonova or macronova. This is the reason why, yes, because of the observations that we were able. So it was really exciting because for the first time we could actually say something about the production sites in the cosmos for all the elements that you're seeing at the bottom of the periodic table. The next discovery that we were able to say, and this is something that Jaap mentioned, is one of the most basic endeavors in astronomy is actually measuring the distance out to objects. And we do this because we're using them in some sense as standard rulers to say something about the expansion history, how the universe is expanding, and also the origin of the universe, as well as where are we going. And in the case of gravitational waves, or these binary neutron stars, remember I said we're measuring the 1/over distance from the wave strain. Yes, so we get a measurement of the distance. But from the electromagnetic or the optical counterpart, we could actually get the redshift of the host galaxy. And together with the distance and the redshift, this allows us to measure this special number, which we call the Hubble's constant, which basically denotes the sum of the different energy densities of the universe. So things like dark energy, as well as matter, etc., and the curvature of space. Okay, so we could actually, from that one event, actually measure, and we call this the first standard siren measurement of the Hubble's constant. And what is hoped for in the future is that multiple events will allow us actually to start to do an independent measure of the Hubble constant. At the moment, there is a tension in cosmology from measurements coming from the cosmic microwave background radiation, as well as actually just using standard ruler measurements. There's about a 5 sigma tension where cosmologists are quite working very, very hard now to understand what exactly can explain. Is there something wrong with how we understand our lambda cold dark matter model of the universe? Okay, so this is one way that gravitational waves can help. Now, our fourth science run started after 3 years of being offline in May 2023, and there are actually events happening and they're being released to the public. You can actually download the apps if you Google for them. You can also see them appearing every night or every day, and we have about 130 additional alerts since then. Okay, so this plot I showed earlier only has the 90 that we discovered until 2020, but we have about 130 additional alerts, as well as one event that's been published, which I'm showing in red here. Okay, another very exciting, exceptional event. But since 2017, a lot has been happening on the observational side, which is what I'd like to end with. Okay, so we have now entered this new era on traditional astronomy, on the electromagnetic side of what we call time domain astronomy. Previously, we used to just look at the universe and we would have snapshots of the universe, yes? what we have now built and what are coming online are essentially huge telescopes or new telescopes that are allowing us to make movies, okay, of the universe, yes, so that we can really be able to see the most violent, the most short time scales, the most rare events, yes, because otherwise previously it was just a serendipitous discovery. If you were looking at that part of the sky, would you see it? Okay, so we have telescopes such as Black Gem, which is Dutch-led from Radboud University happening, which is allowing us actually to, and is dedicated to follow up all gravitational wave mergers, as well as huge projects, the Large Synoptic Skies Telescope, the Vera Rubin Observatory, as well as in the radio, the Square Kilometre Array, and all of these have Dutch participation, but they're really allowing us to have this multicolored, multi-frequency, and some of the science goals of these instruments is to go after future gravitational wave mergers. Now, on the gravitational wave side, on the ground, as I mentioned, we already have the Japanese detector coming online, LIGO India, and future upgrades of our current ground-based detectors. But in the 2030s, there are two projects that are being pursued internationally. The Cosmic Explorer project, which is a gravitational wave detector with arm lengths of 40 kilometers, not the 4 kilometers of LIGO, but 40 kilometers in the US. Or the Einstein telescope, which may be built in this Limburg region, which is essentially interferometer, of 3 nested interferometers, so it's a triangular configuration that will be built 200 meters underground and potentially with 10-kilometer arm lengths and cryogenically cooled. Okay, and why is this so exciting? I'm going to show you, but I just think it's amazing, is that it will be a sensitivity of 10 times that we are trying to get with the LIGO detectors and the Virgo detectors at the end of this decade. Okay, and what does that 10 times sensitivity mean? I told you we had this 1 over distance to the dependence. From the wave strain, it means basically a 10 cube in volume. So that's 1,000 times more in terms of the event rate. So I'm going to show you what that will imply. But on the space side, we are also, and this has been adopted earlier this year by the European Space Agency, the LISA mission. This is the Laser Interferometric Space Antenna, which will be launched in 2034. Okay, and what you are seeing here, this triangular, this is 3 spacecraft, okay, with arm lengths of 2.5 million kilometers, okay, that are cartwheeling in this heliocentric, so that's going around the sun, trailing the Earth. Okay, so I'll show you. Oh, sorry about the music, but you get an idea. Okay, and this will actually be trying to measure supermassive black hole mergers, as well as gravitational waves from white dwarf binaries, as well as potentially signatures from the early universe. Okay, so the landscape in the 2030s is really changing, both on the ground and space for gravitational waves. And what are the implications, okay? So this is a very busy plot, which I'm going to end my talk in explaining a bit. But this donut plot, what you're seeing in the yellow are all the neutron star, pairs of neutron stars merging that are observable in the universe per day, okay? In white are all the pairs of black holes merging per week that will be detectable. And in the orange, the pairs of supermassive black holes that we will be merging within a decade. Okay? And this radial coordinate of this donut is basically the horizon distance, or the look back time you can see in billions of light years. And what you can see in the 2 stars in the middle are the 2 events that I've spoken about. So they're very close by, this neutron star binary in yellow, and the first binary black hole in white. And the curves here that you see in different lines, in green is the Einstein telescope, so how far it will be able to go and see out, as well as in red in LISA, and in blue is what we expect to reach by 2030. So what I'd like to stress is that with the Einstein telescope, we will essentially be seeing all the binary black hole mergers in the cosmos, okay, all the observable ones. In the terms of pairs of neutron star binaries, we are talking potentially about 100,000 mergers per year. Okay, I talked to you about one binary black hole and one binary neutron star. Here we're talking about just transformative numbers, yes? 100,000 neutron star mergers per year detected by instruments such as the Einstein telescope that may be built here near Limburg, okay? And it's just, I think it's mind-blowing, yes? It's beautiful, it's mind-blowing. It keeps me up at night, aside from my 1-year-old baby. It's definitely something that I think we as a community, we were so focused about the first discoveries, the first detections, the 1, 2, now we have 100 or 200 events, yes? But we're really talking about tens of thousands of these events happening per year, and potentially in the 2040s as well as the 2030s with the space-based LISA interferometer. Okay, so it's a transformative time for gravitational waves. And of course, this means that a lot of these systems will not be visible, even the binary neutron stars, by traditional telescopes. We can only see the closest by ones with the most advanced telescopes that we're building in the 2030s. So this really is why gravitational wave astronomy is a new type of astronomy. We will be able to see things that just are totally inaccessible through normal traditional methods using light. Okay? And so we can study the large-scale structure, how structure evolved, how our universe came to be, using these systems as probes, not just studying them individually, but using them also as basically lampposts to understand how galaxies, how our universe came into being. And so we can really go into an era of precision physics, precision astrophysics, how are black holes driving the evolution of the universe? How do the fundamental laws of physics interact in this dynamical, strongly curved space-time? What's the intrinsic nature of these black holes and neutron stars? And I will end there. I am showing here the entire gravitational wave spectrum that spans decades of frequency space. I have just talked about the high frequency end. Yes, I'd really like to stress that we have observations already coming from pulsar timing arrays in the nanohertz regime. We have the millihertz regime where we'll be observing supermassive black hole binary mergers. And many of these systems also have electromagnetic counterparts. So the future is both bright and loud. Thank you very much.
Thank you, Samaya, for this astonishing lecture and for these beautiful animations, these very insightful animations. One question I have is how often do these gravitational waves go through these detectors? Is that every second or?
Yeah, so in the era of Einstein telescope, we expect there to be overlapping signals, yes? So typically, they may last minutes to tens of minutes because the detectors will actually be going down to lower frequency as well. And so there'll be overlapping signals, but typically these events are happening every couple of minutes in the universe. At the moment, our sensitivity of our detectors means that these alerts we're seeing a few per week, okay? When in 2015, when we first turned the detectors on, they were at a factor of a few less sensitive than they are now. So we were seeing, you know, one a month or so. Yes. So as the detectors increase in sensitivity, we are increasing in terms of detection rate. Yeah. So at the moment, if you download your apps, I mean, it's kind of amazing because when the first event happened, I'd been working in gravitational waves for 15 years. Lots of people felt quite sorry for me. They thought it was a very fringe the science. I had quite prominent colleagues come to say to me, oh, maybe you should think about spending your time working on something, you know, more real, more, this is a bit science fiction, all of this gravitational wave stuff, because people just, I mean, we believed that they were out there, but whether we would actually ever detect them or observe them was, you know, many people were highly skeptical, and many scientists, many physicists and astronomers were highly skeptical that they could be detected. And indeed, when this first detection happened, you know, we worked in secret for about 6 or 8 months before the announcement was made. You know, we scrutinized everything. We really made sure that this was a real cosmic event. And to me, it was amazing that 3 years later, you know, given, this mind-blowing first event, already 3 weeks later, when I would get alerts on my phone or wake up in the morning and see, oh, another binary black hole is detected. And you think, oh my gosh, you know, a few years ago, it was mine, you know, just the world, you know, my world stopped, and now we're already in this stage where, oh, it's another one, oh, it's another one, yes, it's another pair of black holes merging, and it's a totally different period. But, you know, of course, with the next generation of detectors, I think it's just going to become,
So the Einstein telescope will add even more and more.
Yeah. And I think the whole world is just so excited about what could be potentially happening in the Limburg region, because this really is the next frontier for the field, yeah?
Yeah. Okay. If there are any questions, please raise your hand and I'll come running to you. If you have a question, then I will come to you.
Yeah. So thank you very much for the lecture. I had one question. So you were saying in almost the last slides where you were showing these amount of the number of binary
This one?
these binary neutron stars that would happen, that we would be able to detect in the next 20 years or so. It says 10,000 billion light years, right? But didn't the Big Bang happen about 13.8 billion light years ago? So what does that scale mean?
Yes, so that really is just a scale that's, you know, showing potentially how far we go back. But you're totally right, yes, in some sense. But we will be able to basically see, we think that that stars formed around a redshift of about, you know, 15 or so, but these gravitational wave detectors will actually go beyond that kind of detection threshold, yes? So we will be able to see if black holes are created basically from the early universe, yes? If they're not coming just from stellar mass regimes, yeah. But you're totally right, yes, the scale is just put there just to show essentially the logarithmic scale of the radial look-back time.
Yep.
Thank you very much for your lecture. I had a question, which is maybe a bit of a basic question in your field, but as a law student, I'm not really up to date. I was wondering, what exactly is an event horizon when you talk about a black hole, and do this have any impact on the gravitational waves? Thank you.
Thank you, that's a great question. Yeah, the event, as I mentioned, black holes themselves don't have a surface. Neutron stars, they have a surface, as we understand. Black holes are essentially cloaked by the event horizon, whereas it's essentially where light cannot escape from within this cloaking, yes, of this region of the space-time that is basically shrouded to us, yes? We expect that light cannot come from this event horizon. So indeed, there are people who are now using gravitational waves and theoretical kind of quantum gravity people saying, okay, can we actually say something about physics that may be beyond our current understanding, for instance, of the Standard Model, or beyond general relativity effect, using peculiarities that may happen near the event horizon, or indeed if these are not black holes, if these are more exotic compact objects, could we see deviations, yeah? But indeed we are treating these more as macroscopic objects, and so this is still I think the next frontier of what people would like to do with things like the Einstein telescope, because the signal-to-noise ratio would be so great in that case that we can, in some sense, use these as precision instruments. Yeah.
Any more questions? Yes. Wait, I will come to you later on. First, this question.
Sorry, I think it's a very basic question. Maybe I didn't get it. But do you always need to have two black holes or two neutron stars that interact, or you can have just one that spins and also generates this? And so the second question for the gamma ray bursts is kind of the same thing. Do you always need two, or can you just have one star that dies and creates this? Thank you.
It's not at all a basic question. It's a really excellent question. So indeed, what you need to have gravitational wave emission is basically a non-symmetric accelerating mass, basically, yes. So because we have these pairs of black holes going, they're acting as these rotating dumbbells, yes, and causing this non-symmetric sort of mass distribution in the space-time, creating gravitational waves. But as you said, we can actually have, and we are looking for, neutron stars that are just single, yes, that are just rotating around each other, that may have deformities, okay, that are causing this axis, this non-symmetry, asymmetry in the system, that can also emit gravitational waves. So we are searching for not just collisions and mergers of these events, but looking for these long-lived, what we call continuous wave signals, which are coming from things like neutron stars. We haven't detected any yet, but we have put upper limits on what basically the ellipticity or the asymmetry of these neutron stars could be, because they can also emit gravitational waves. Also, with regards to your question for gamma ray bursts, indeed, we expect to see them at the end of the life of massive stars in terms of long gamma ray bursts, yes? And so we do think, yeah, that there are also people exploring the potential of seeing maybe gravitational waves from these kind of signatures as well, from core collapse supernova. The issue, so you can see there's a core collapse, a supernova simulation. The issue there is that we're really limited mainly to our galaxy. And so there we expect to have one every 50 years or one every 100 years, so that's why the rate. But if there is one, we will be able to, yeah, I mean, it will be mind-blowing. So indeed, there are many sources that we have not seen, that people are actively searching for, and that are developing predictions in order to make sure we can pull out the maximum physics.
One moment, please. Wait for the microphone, I will come to you.
If binary is most common, do triples also are there?
Yeah, excellent question. So we know that most massive stars exist in pairs, but we also know that they exist in triples and maybe quadruples. So I have colleagues that are looking into the fact, could some of these systems have come from a triple system? At the moment, we don't know if there was a triple system where one of the objects was ejected out, but initially it was in a triple or a quadruple system. There's nothing in terms of stellar evolution that says that it is impossible. There are two main formation, broadly speaking, two main formation tracks we think of in terms of stellar evolution, if they're in pairs, in isolation, developing, or whether they're in dynamical environments such as globular clusters or young stellar clusters, where you can expect there to be many more interactions happening. So indeed, that's something that statistically we want to be able to say when we have thousands of events, yes? What is the formation channel? Are they coming potentially from triples? Will we be able to distinguish that from things like the eccentricity, the spin of these systems, etc., if they're not in circular orbits?
Thank you for your lecture.
Oh, thank you.
So I'm not in this field, so excuse me if my questions are a little bit elementary. But so I have two questions. The first one is related to the video you played of the LIGO detector. So it had these two right-angled, this split laser. And you discussed that that's the sort of the perpendicular squeezing and stretching of the gravitation that's caused by the gravitational waves. So I'm assuming that then the source of the gravitational waves would have to be above or below. Do you see what I mean? Because what if it came at a different angle? Because it's
yeah, we have
right
ways
angles.
to disentangle if it's coming from a different angle.
Okay.
But it's just very simple in terms of describing the effect to
Right.
think of it coming as perpendicular, because then you see basically the arm lengths. You can kind of visualize this stretching and squeezing, but in actual fact we are measuring a combination of those two polarizations, the H plus and the H cross, if you remember that kind of digestive colon thing, the slinky, the blue, you're measuring a combination, and then we disentangle the polarizations from the wave strain that we're measuring, yes, the flickering of the light.
So does that affect the sensitivity at all?
Yes, it will affect the sensitivity.
Okay.
So if it's coming directly above, we will have a much higher signal to noise ratio. And indeed, sometimes if the wave is coming this way, yes, we have much less sensitivity, yes. So it totally does depend on kind of the inclination angle or the orientation of the source with respect to the detectors.
And my second question was related to the diagram you showed of with all the different detectors and how that would expand our sensitivity and going into the 2030s. So you mentioned this LISA detector, and I'm curious. I mean, to my understanding, right, a supermassive black hole has more mass than a stellar mass, but somehow the other detectors can't detect it, and yet that's something that's unique to LISA. Why is that? Because
of the frequency range that these detectors are operating in, yeah. Sorry, so here, in the high frequency range, in the on ground, we are detectable to basically stellar mass mergers. Okay? Now LISA, because of the arm length, yes, 2.5 million kilometers between, so it's basically 3 detectors in a triangular configuration, in a nested configuration, will be measuring the millihertz regime. Okay? And if you consider basically the frequency, if you think back to maybe high school or first year physics, if you just think of two objects going around in a Kepler orbit, yes, the frequency depends on the mass as well as the radius, yes, or the separation of the objects, and that is what basically sets what mass as well as how far away to each other the systems can be.
Right, that makes sense.
So LISA's working in that millihertz regime, and so we're measuring masses of supermassive black holes of about 1 million times the mass of the sun. Okay, now in the nanohertz regime, we have these pulsar timing arrays, so we basically have a galactic gravitational wave detector using neutron stars themselves, okay, and by measuring the time of the arrival of the gravitational wave from a background of supermassive black holes, we think of about 10 to the 9. Yep, so 1 billion times the mass of the sun, so at a much higher mass range.
Yep, thank you.
No worries.
Thank you very much. I have 2 questions, please. The first one, I understand that as the wave will hit the planet, the distance will change and the laser will need more time or less time to go in the tunnels. My question is, do these gravitational waves also affect time? Because it's space and time that is impacted. So how does it work? Maybe it's a technical question, I don't know. We cannot assume that the time will be the same in the tunnel. So how do we make the difference between the impact on the distance and the time?
Yeah, no, that's an excellent question. On the Earth, because of the Earth's gravity, we are able to think of 3-dimensional space as well as time, yes. But of course, when we talk about going near a black hole, that is when strange things start happening to our idea of, what do we mean by time or space, yes, But you are totally right that indeed, it is in some sense a technical question when we talk about using the laser light, yes, to measure the distances, because indeed when you go through the maths, and I showed that delta L over L, that is done in general relativity where we are taking into account the four-dimensional space-time, yes? So we are really using, we are taking into account that, but on Earth we have kind of much more Newtonian gravity where you can see the separation of space and time.
Thank you. My second question, I need your help to understand. You used a slide a bit before that one with a red frame highlighting one specific event that you talked about, right?
This one?
No, previous. Yes, this one.
Yes.
So I understand that the y-axis is about the mass involved in the event. What I do not understand is the x-axis.
Yeah, there is no significance to the x-axis.
Okay.
It's just a way to depict these sources. So there is actually, and this one event is the only event that we have actually published from the 4th science run. It was exciting because one of the events, one of the progenitors, so one of the pairs of the objects we believe is a neutron star, but the other one we don't know whether it's a neutron star and black hole. And one of the things that makes it exciting is that before gravitational waves or this event happened, we actually thought that there would be nothing there, that black holes would not form under 5 solar masses. Whereas in this case, it seems that actually we can basically fill this region in space, which theory actually predicted was not the case.
Thanks a lot.
Yeah, let's do 2 questions and then 3 questions maybe, and then we will end.
So thank you for the lecture. It was very nice. Throughout this entire talk, it felt very intangible. We're talking about a million billion light years away. And as an expert in your field, of course, you have equations and physical laws and stuff like that to back it up. But from a more, I guess, like human perspective, how do you make it more tangible, or how can you kind of believe it more, right? So the distance, and to basically bridge the distance, and also what is the limit to what we know currently?
The limit to,
I guess, what is possible to observe, because these trillion or billions of light years away are of course very far away. So can we go beyond that, or is that the limit?
Yeah, okay, great question. So I think your first question was, it's quite intangible, yes, these distances. Indeed, I think when we talk about gravitational waves, yes, we are talking about astrophysics and understanding the cosmos, and in some sense that is about, fundamental physics. This is very fundamental, you're trying to understand the origin of the universe, or what's the nature of gravity, or what's the nature of black holes. So in some sense, these don't directly relate to our everyday life, that's true. In terms of being able to measure those distances, everything about general relativity that we understand at the moment, at least at the macroscopic scale, seems to be a very beautiful theory that we have tested and confirmed many times, yes? And so when I talk about those distances, we can actually pull that out of the signal just from measuring this wave strain, yes, this 1 over distance to the source. So that's what's giving me, I'm using these systems as a ruler, and this wave strain that we're measuring, I immediately get the distance to the source. So that's what's giving me this 1.3 billion light years away, or 130 million light years away. But you're right, it is very, I think, awe-inspiring that you see this tiny wiggle, and that we can connect it to something that is just happening so far away. Now, why is it useful? Well, it's useful because before gravitational waves, we didn't know whether pairs of black holes existed, whether they merged, Yes, we didn't know whether we would actually be able to detect gravitational waves, yeah? And this really is allowing us a totally different way to measure things like their masses, as well as the spins, the fundamental properties of these kind of punctures in the fabric of space-time. Okay, this is really the frontier of, you know, science, yes, in some sense, of understanding the fundamental laws. So because of this, I think they are very useful in terms of where we are going. And what we are currently limited is basically the sensitivity of these detectors. So we could observe them, we could roughly say the masses are this, we could roughly say the distances, but actually the signal to noise ratio of these events, you know, you can see it visibly by eye, some of them, the strongest sources, but you can't, you don't have very good parameter inference, or you are limited basically by the noise of the instrument at the moment. Now in the future, we will be talking about the signal to noise ratio of these events going from tens to thousands. Okay, and there we will really be able to start doing exquisite measurements. So then I think it becomes very interesting on a physics idea, yes, not only testing general relativity, but also testing something about particle physics, how we understand the standard model of physics, and then also just using these also as astrophysical probes, and also using these to actually say something about the origin of the universe and where we're going. Yes, so I think that is where the hope is. And also when you have statistically many, many more, then you are able to start to actually say something. Yes, similar to when we do like population statistics and understand demographics and the environments and census, you know, we can start to say something quite profound, yeah?
Thank you.
We have time for only one question, I'm afraid, and you were first, so make it a good one.
Hello, thank you for your presentation. My first question was just the chirps. How do we distinguish a binary neutron merger instead of a black hole?
Yeah, that's a great question. So actually, let me go to one here. Did I show the chirp signal? Yeah, here. So basically by measuring the gradient as well as the frequency band, yes, the gradient, the slope of this chirp, as well as the frequency band, we can actually say something about the masses of the system. We call this the chirp mass. It's a combination of the two masses. Okay, so by measuring basically how the frequency is evolving as a function of time through the slope and the frequency itself, as well as where it goes out of band, where we think the merger happens, we can say something about the separation of the objects just before, whether they merged in the frequency band of the detectors or outside. So in this case, because it was 0.2 seconds in the particular frequency band, as well as the slope, suggested we were looking at systems of tens of the solar masses, and we saw the merger. Now in the case of the binary neutron star, here, we could actually, sorry, I'm going to just show this. From here, from the slope as well as the frequency band, okay, here, we could actually say that this combination of the masses meant that it was about 1.12 solar masses, this chirp mass, which either implied it was 2 neutron stars or a neutron star black hole or 2 white dwarfs, but then it actually went out of band and the separation was tens of kilometers, okay, if we use the masses that I mentioned. So we knew it was not a white dwarf because white dwarfs have radii similar to the Earth, so thousands of kilometers. And so this is what led us, just by looking at this spectrogram already a few minutes after the event, to say it's most likely 2 neutron stars because of the combination of the two masses, as well as when it went out of band, the separation being tens of kilometers.
Okay, thank you. And my second quick question is just the the mirrors that reflect the lasers, how are they probed to be able to detect the gravitational waves? Like, how are they that sensitive? Or like
yeah, it's a great question. So I think decades of work in understanding all the other noise that can cause or mimic a gravitational wave signal. So a plane going over the detectors can cause basically the mirrors to basically start to move, yes. Somebody walking past can cause the mirrors to move, yes. The American detectors, one of them was built in Louisiana because the governor, politically, they supported the development of this gravitational wave detector because it brings in new jobs, in infrastructure, etc. But it also happens to be where trees are being logged all the time, yes? So you can imagine all the time there are noise sources coming from basically trees being cut all the time, yes? And so this is something that has taken really, I would say, a couple of decades, yes, to understand all the other noise sources, yeah, and to be able to actually and characterize basically the sensitivity of these detectors. And it's an ongoing effort. We're now using machine learning techniques to be able to do that. But indeed, the fact that the first event, the fact that we had 2 detectors, okay, on basically thousands of kilometers separated, and the detection, the arrival time at the detectors was consistent with each other relating to this cosmic source, that gave extra confidence, yes? So the fact that we have a network gives confidence to it being actually an astrophysical event and not just something locally or due to the seismic motion of the Earth or ocean waves, etc. But yeah, it is a really non-trivial process to understand all the noise sources. And, some people have said, these are the most exquisite kind of earthquake monitors that we have, yes, because we are really using them in terms of understanding the seismic motion, yeah, of the Earth as well.
All right. Thank you for this amazing lecture, Samaya. Please give her a warm round of applause for last time.